Hi, Math 30-2. Welcome back to Permutations and Combinations. We're going to take a look at Lesson 3 today, solving permutations with restrictions. So if you remember from last day, we saw a couple questions that did have restrictions in them. And the key thing is that we always deal with the restrictions first, okay? So that's what you're going to see with these questions. I always deal with the restrictions first. And then whatever's left in the remaining part of the problem, we solve like we kind of did in last day's lesson, okay? And again, if you remember from last day's lesson, permutations and the fundamental counting principle are kind of one and the same. We can usually use either method to solve a question that we are dealing with permutations. And you'll see that today. Sometimes we'll use the fundamental counting principle. Sometimes we will use permutations. Again, that's not the only way to solve it. It's just the way that I'm going to show you. If you your brain kind of thinks the other way and you think there's a different way that makes more sense to you, then by all means, please do that. And if you have a question as to whether or not that's a valid calculation or a strong mathematical process, then by all means get a hold of me, email me, and I can let you know if it works. Okay. So just like it says at the top here, permutations with restrictions, many of the problems in this lesson can be solved using the fundamental counting principle. Okay, so class example 1 here, we'll just get into questions, looks like this. Answer the following question using the fundamental counting principle and then factorials. Okay, so remember that's our exclamation mark in mathematical notation and symbols. In how many ways can all of the letters of the word oranges be arranged if A, there are no further restrictions, and then in B, the first letter has to be an N? So again, remember what we want to talk about first is the number of elements or things that I am trying to arrange or order. So in this question, that would be the letters in the word oranges. So I have 1, 2, 3, 4, 5, 6, 7 elements, 7 things to arrange. So how many ways can I arrange those 7 things if there are in A no further restrictions? Well, they say use the fundamental counting principle, so that would mean I have 7 blanks, 2, 3, 4, 5, 6, 7 blanks. And the first option, there would be 7 choices, then 6, then 5, 4, 3, 2, and then finally when I get to that last blank, there would be 1 choice left. So if I multiply all those values together, okay, 7 times 6 times 5 times 4 times 3 times 2 times 1, okay, I will end up getting 5,040, okay, as my solution. They also asked me to do that using factorials. Well, if you take a look at this calculation, 7 times 6 times 5 times 4 times 3 times 2 times 1, in factorials, that's just 7 factorial, okay, which will obviously also give me 5,040. Okay, so just 2 different ways of writing the same thing. Okay, now in B, they have a restriction, and the restriction is that the first letter must be an N. So if I'm going to show you this using the fundamental counting principle, this is what it would look like. I would obviously still have 7 blanks to fill in. 1, 2, 3, 4, 5, 6, 7. But the first letter has to be an N. So what you do is you make that happen. So one of 2 things. Some students will go like this. They'll put a 1 there because there's only 1 N in the word oranges. Other students will do this. Instead of putting a 1 there, they'll actually put the letter N there. Okay? Either way, you're going to get the same calculation. So what happens is this, is that if I put the N there, it's basically out of the mix now because I have used it and placed it in a specific spot. Therefore, when I go and do the remaining calculations, I would have 6 choices, then 5, 4, 3, 2, and 1. So that's what that calculation would look like. So now, when I do 6 times 5 times 4 times 3 times 2 times 1, you are going to get 720, okay? And that calculation in factorials, okay, the 6 all the way down to 1 is just 6 factorial. So that's what that calculation looks like in factorial notation. And again, that will still be 720. So I've kind of written the calculation out in both ways that they requested, the fundamental counting principle and using factorials. All right, next question. Class example 2. It says 3 girls who they label as G1, G2, and G3, and then 4 boys, B1, B2, B3, and B4, are to be arranged in a row for a photograph. In how many ways can this be done if there are no restrictions as to where each person stands? Okay, so again, Very similar to the last question where we were arranging the letters in the word oranges. Here I'm arranging people, okay? Doesn't really matter here in terms of the arrangements. I have 7 people to organize in a photograph. So how many ways can I arrange 7 people or 7 things? 7 factorial, okay? So 7 factorial is just going to be 5,040, okay? I steal that calculation from up above. B says the photographer now decides that he could take a better photograph if no 2 people of the same gender can sit together. So obviously that means we have to now alternate boy, girl, boy, girl, boy, girl, boy, girl, okay? So I have 4 boys and 3 girls. That means I'm gonna have to start with the boys because there's more of them. So in the spaces that they've shown below, it would have to look like this, right? I would have to have boy 1 here, then I'd have to skip a space, boy 2, skip a space, boy 3, skip a space, boy 4. Okay, again, I have to put the boys there because there's more of them, leaving 3 spaces for the girls. So girl 1, then girl 2, and girl 3. Okay, that's the only way I can alternate gender. So determine the total number of arrangements that the photographer could take. So what would the calculation look like? Well, again, when I go back up above to that diagram, I would have 4 options to put in this space for a boy. Then I'd be down to 3, then 2, and then 1. With the girls, okay, I would have 3 options for this space, 2 options for that space, and then 1 option for that space. So when I take a look at the boys, then, okay, the boys would be 4 times 3 times 2 times 1. That's 4 factorial. The girls, okay, 3 options times 2 options times 1 option, that's 3 factorial. So basically you would take these 2 calculations, okay, and you're just multiplying. Everything in this question is multiplication. There is no adding or subtracting. So it's 4 factorial, 3 factorial, okay, that's going to be 144, okay, as a total calculation. In class example 3, 6 actors and 8 actresses are available for a play with 4 male roles and 3 female roles. How many different cast lists are possible? Okay, so in this question, this would be a permutation because when you play a different character in a play, that would be a different order, okay, in terms of order matters. When we start giving positions to people like actors, actresses in the play, or there's a president and a vice president, those types of things in organizations, order matters, right? So again, it's not just being part of the group, it's a specific role in that group. That is a permutation. So when we take a look at, let's start with the actors, okay? There are 6 actors, okay, that can be chosen from, and I need to pick 4 of them for the male roles, okay? So there are the male roles. The female roles, there are 8 actresses, and we need 3. We need to select 3, okay? So what I'm going to do is I'm going to multiply those 2 together. So again, the 6p4, that is the actors, okay? And the 8p3, that's the actresses. Okay, and again, we would be saying and, we would not be saying or. I need actors and actresses. So when I do that calculation, I get 360 for the 6p4, okay, and 336 for the actresses. So when I take those 2 values and multiply them together, you get 120,960. Okay, so there is your final calculation. All right, turn the page. Now on the next page, it says Andrew is asked to determine the number of arrangements of the letters of the word brains, okay, in which the vowels are together. Okay, so that's the key thing here in this question. They're saying the vowels have to be together. That's a restriction. His reasoning is shown as below. So since the vowels must be together, he's going to treat A and I as one element. So he kind of sticks them together, and that is what we are going to do in these questions. When they tell you some things have to be together, we kind of stick them together with glue, and we treat them as one thing. This means I now have 5 elements. So why would he have 5 elements? Well, because there's actually 6 letters in the word brains, but he's sticking A and I together, so we're treating them as one letter. So he's thinking there's 5 things to arrange. Okay, and he's correct in that thinking. So his 5 elements are A and I, that's 1, B, 2, R, 3, N, 4, and S, 5. So in his mind, he's saying, okay, well, how would I arrange 5 things? Well, he's right. 5 factorial, okay, would be the number of ways I can arrange 5 elements, and that gives him a total of 120. So I like his reasoning there, but he is missing out on something here. So in A, it says, is Andrew correct in saying A and I should be combined as one element? Okay, and the answer says simply just yes. Okay, that's what we want to do. When things have to be together, we stick them together and treat them as one thing or one element. But here's what I was talking about. It says, Andrew's final answer is not correct. Explain what is missing from his reasoning and determine the correct solution to his problem. So in the question, you have to be very critical when you read. Here it says the vowels have to be together, okay? But it does not say they have to be together in the order A and I. So for example, if you just look on the side of B here, A and I, those are the vowels being together, but so are I and A. Okay, so in both those cases, A and I are together. Some questions will say in a specific order, and in that case, then that's a different thing, okay? And I will show you that likely in a question coming up here. But in this question, it just says the vowels have to be together. So what we do is basically the following calculation. We go 5 factorial, okay, which he was correct on saying. So there's his 5 elements. But what I have to do now is I now have to multiply it by 2 factorial. So the 2 factorial, okay, that refers to the number of ways that the things are stuck together can be arranged. So what I'm saying is that 2 factorial refers to this AI, okay? Because AI, there are, if I take a look at this calculation, right, those two things being stuck together, there would be 2 ways and then 1 way to arrange the AI. Okay, so that's 2 factorial, isn't it? So the first number refers to the total number of things you are ordering. The second number refers to the number of ways the things that are stuck together can be arranged. So he's correct in his 120, that's the 5 factorial, but now you have to multiply that by 2 factorial, which is 2. So there are actually 240 ways, okay? So that's the piece he's missing out on. He only had half of the number of ways to order those letters. Okay. Next, find the number of permutations of the letters in the word kitchen if K, C, and N must be together in the order K, C, and N. So here's what I was talking about, right? So first thing is K, C, and N have to be together, and they want them in the order K, C, and N. So in this one, I would not have to worry about rearranging the number of ways the things stuck together can be ordered, okay? So again, here's the first thing I do. I count the number of letters in the word kitchen. 1, 2, 3, 4, 5, 6. There are 7 letters in the word kitchen, but I am going to be putting K, C, and N together, treating them as one letter. So what I really have is I have this, right? I have K, C, and N. That's kind of like one letter, right? So K, C, and N, that's one letter. I have left an I, a T, an H, and an E, okay? So in total, I am going to be arranging 5 things, okay? So if I arrange 5 things, how do you order 5 things? Well, 5 factorial, that's your answer. So in this question, it's just 120. Again, I do not need to multiply by the number of ways I can order K, C, and N because they say K, C, and N have to be in that order. Now, if you look at B, it says K, C, and N must be together, but not necessarily in that order. So what you would do is the very same calculation that we did in A, so 5 factorial. But this time I have to multiply by the number of ways K, C, and N can be organized. So K, C, and N, there are 3 things there. Okay, that can be organized 3 factorial ways, right? 3 options, 2 options, 1 option. So I multiply by 3 factorial, okay? Because K, C, and N have to be together, but they can be together in any order. So now that's 120, okay, times 3 factorial. That's 6. 3 times 2 times 1. So that's a total of 720, okay? So again, in those questions, the difference is this. This one has in the order K, C, and N. And this one is not necessarily in that order. So they, as long as they're together, okay, then you have to multiply, okay, by the number of ways the things that are stuck together can be organized. All right, last question for today, and then you'll have some time to practice this. Frank, George, Hannah, Iris, Jacob, and Kim have playoff tickets for a hockey game in adjacent seats A3 to A8. In how many different ways could they sit together in A3 to A8? So the first thing I want to make sure of in this question is that the number of people matches the number of seats. So I have 1, 2, 3, 4, 5. I have 6 people, and A3, A4, A5, A6, A7, and A8. That is also 6 seats. So the 6 people are going to go into the 6 seats. So how many ways could they sit in those 6 seats? Well, there's 6 people. So 6 factorial is going to be 720. Okay, so I have 6 seats to fill, 6 options for the first seat, then 5, then 4, then 3, then 2, then 1. Multiply those values together, that's 6 factorial, so 720. Now, George and Hannah are dating. And how many of the arrangements in A would they be sitting together? So again, this is where you want to draw parallels between this question and ones that we just did. So basically all they're saying here is that George and Hannah, okay, are going to be together. So we're going to treat George and Hannah kind of as one element, okay? So again, notice it doesn't say George and then Hannah. It could be George and Hannah or then Hannah and George. So in this question, I will have to multiply by the number of ways George and Hannah can be together. Okay, so I'll show you that in a second here. So now George and Hannah are one element or one person in this question. So instead of having 6 people, I now say I basically have 5 people because George and Hannah count as one person. And then the number of ways George and Hannah can sit together are 2 factorial because every arrangement I have could be George and Hannah or Hannah and George. So that's going to be 120 times 2, so that's 240. Okay. Now, just before the game, George and Hannah have a disagreement and decide not to sit together. And how many of the arrangements in A would they be sitting apart? Well, that's where your calculations in A and B kind of come into play because in A, that's all possibilities, right? That's every single possibility. I'm going to take the calculation in A and subtract the calculations in B because B is where they're always together, isn't it? So if I take every single arrangement and I subtract all the ones where they are together, I'll get the ones where they're not together. So that is 480, okay? So that's the easiest way to do that calculation. A was all possibilities. B was all the possibilities where they're together. So if I subtract, I'm left with all the possibilities where they are not together. Okay, so hopefully that made sense. Again, the basic thing today is that you deal with the restrictions first. Okay, if things need to be stuck together or beside each other, then treat them as one element. If they tell you it has to be in a specific order, then your calculation is done. If they tell you that they just have to be together but not in a specific order, then you must multiply your calculation by the number of ways those things together can be arranged. Okay, so practice that. And again, let me know if you have any questions moving forward. All right, have a great day, you guys. Bye.